page 125. Yes, sir. Please go. All right, page 125. Yesterday, or 2 nights ago, I should say, for homework, you did word problem 82. We didn't have opportunity to go over that in class yesterday, so we're going to go ahead and go over it now. So if you would, find the homework from 2 nights ago, word problem 82, and if you would go ahead and read word problem 82 for us. Actually, it was 82 last night. I need to make sure I've got this right. Yeah, 82 was 2 nights ago. Go ahead and read word problem 82 for us, if you would, Gavin.
Gina has 24 quarters and dimes that total $5.10. How many of each coin does she have?
Obviously, the two unknowns are
Quarters and
quarters
dimes.
and dimes. And it doesn't specify which one should be X, right? It doesn't say 12 more dimes than quarters or anything weird like that. It just tells me what about the number of quarters and dimes. 24 of them total, so we should let one of them be, and the other,
Total minus X.
which in this case would be,
Dimes.
well, 24 minus X, which is the total. Which one did you choose to be X?
Well, I would pick quarters, but for some reason, I looked at 85 for 82.
All right, so we should have let quarters be X, right? And then dimes, you said, would be the,
24 minus X.
there we go. That's the number of each. We also need to account for the varying values of quarters and dimes. Of course, we know that a quarter class is worth 25 cents. Now, if we're representing it as dollars, that'd be 0.25. The value of a dime would be, class, 10 cents, but again, that'd be 0.10 if we represented it as dollars. But the last time we did a problem like this, I encouraged you, go ahead and represent it not as dollars, but as cents, so we don't have to worry about the decimal. How many represented it as cents and didn't bother with the decimal? You didn't even do the right problem. Slob. All right, just kidding. All right, so we've got the number of quarters and dimes. We've got the cents of each individual quarter and dime. So now we need to represent the total cents from the quarters and total cents from the dimes. How would we represent this column, Gavin?
25x and 240 minus 24x.
Ooh. What are we distributing?
The 10.
The 10.
So 10x.
Minus 10x. There we go. All right, again, I encourage you to do the distribution here. Now, if we take all the cents from the quarters and all the cents from the dimes, Maddie, it should add up to how many cents? Well, what should it have been? I don't care what you did. Now tell me what you should have did. Are you looking at the word problem, number 82 in your textbook? All right, how much money does Gina have? Right, but my question was, how many cents does she have? There we go, 510 cents. So we know the quarters have 25x cents. The dimes are 240 minus 10x cents. But total, she has 510 cents. What's my equation? There we go. Was this your equation by any chance? All right, so at least one of you got it. All right, we'll combine our x's together here, then Noah, to get 15x. At the same time, let's move the 240 over as a, to get, and when we divide both sides by 15, we'll get x is equal to 18. And that means that Gina had 18 quarters and 6 dimes. And I believe it asked how many of each coin, and it did. So there's our answer, 18 quarters, 6 dimes. So you got that. You did the wrong problem. You good to go now? Did you figure out what it was that you did wrong now, Maddie?
I got it out there, but then I left it.
Oh, so you took it out here, but when it came time to put it here, you put it back in. That's going to mess a whole lot up. Because you had, well, you still moved it twice, I assume. But that meant these suddenly became thousands and hundreds and stuff. No.
I got 18 mistakes, but don't ask me how.
So you made 2 mistakes that basically balanced each other out?
I guess so.
All right. Do you understand what you should have did so that you don't make mistakes in the future? All right, I think that's Brecken. Hopefully he's feeling better. You gonna be all right, or? Okay. Head down to the office and just let Mrs. Keys know. He's not feeling better. Anyone need hand sanitizer? Or a mask? All right. Let's take a look at Liberius. You got your mask. All right. Word problem 88 now. Let's take a look at word problem 88. We're not laughing at you, Bracken, in case you're watching this later. We are not laughing at you. We are feeling for you. In an effort of not feeling sick ourselves, we interject humor into the situation. That's my coping mechanism, right? When something makes me really nervous or I anticipate something not going well, I just start making jokes about stuff. Well, we just had a baby a couple weeks ago, and everything went great. But 2 babies ago, when Renee was born, things did not go so great. My wife was in labor pretty much all day long, and I don't do pain real good, especially when it's pain in somebody else. Like my own pain, I don't like it, but cope with. I feel pain when other people are feeling pain. It's not good, and so I'm not feeling real great about this either. She's in agony, and since I'm not feeling great, what do? I start cracking jokes, and she did not like it. So I was like, man, this is great. This is not good. My only coping mechanism. I'm not allowed to use it now. So anyway, that's just my coping mechanism there, Brecken, so we don't all start vomiting or something. All right, problem 88. We'll work a word problem. What better way to take our mind off of something than doing math, right? Okay, never mind. Maddie, read number 88 for us. All right, so the 2 unknowns here are adult tickets and student tickets. And did it specify which one should be X this time? No, once again, it just gave us a total number. So which one did you choose to be X? Because they cost more. And then the student tickets, good, the total minus X. Assuming we did the correct problem for homework last night, did you guys get this for your number column? All right, then we have the value of each, and what were the values here, Maddie? $4 and $2.50. Oh, man. And they had to do that to us. And then the total value. Well, the adult total is really easy. Yeah, we like that. You know what? I gotta distribute a decimal if I put it here. Now normally I avoid that negative, but I don't like decimals. You know what I'm saying? If I were to flip-flop these, the multiplication would be easier, wouldn't it? I am that lazy. Excuse me. 395 minus X. Because it is 250 and 4, I erased the wrong column. It's 4 and 250, but see now, the student tickets are really easy, class. 250x. And now at least it's a single digit number I'm distributing, right? 4 times 5, class. 20. Carry the 2. 4 times 9 plus 2. 38. Carry the 3. 4 times 3 plus 3. 15. Alright. And of course 4 times negative x. Negative 4x. So now at least it's a little easier. Do you see what I did there? So normally my rule of thumb is bigger value, let it be x, because I don't want to deal with negatives. Well here, I'm like, you know what, I'd actually rather deal with a negative than trying to distribute a 2.5 through all of this. You know what I'm saying? Do y'all see the way my math brain thinks? Because again, my thing is I always find the easiest way to do everything because I'm lazy. So if I can get you to think that way, then y'all have an easier life too. Yeah. You headed home? All right. Pack up your stuff then, and you can maybe watch the video later if you're feeling up to it, and watch us make fun of you and stuff like that. Okay, we weren't really making fun.
At least we can laugh.
Well, we laughed. All right, hope you're feeling better, Brecken. All right, so when we come to our equation, we know this is now again, this is going to look very different from your equation, right? But the answers will still come out the same, right? We've got our 1580 minus 4x plus the 250x, all equal class 2 There you go, $1,154. Now, we do need to combine the x's here. I've got a -4 and a +2 and a half. Picture 4 pizzas. Take away 2 and a half. What do you have left? 1 and a half, right? But it's going to be, keep the signs greater, -1.5x. Do you see it? Now, at this point, I could move this, oh, let's just go ahead and do it. Let's move it over. We're -1,580. That's going to give us negative 426. And since both sides are negative, and again, this is why I was willing to deal with the negatives. Both sides are negative. What do we do with the negatives? Just knock them off, right? At this point, we do need to annex the 0 there, and as we move the decimal over 1 place each, and now we're dividing away the 15 from both sides. 15 goes into 42 how many times, class? 3 times 15, like 15 minutes, that'd be 45 minutes, right? So not quite 3, just 2, because that'd be 30, right? That leaves us with how many left over? 12. 15 into 126. Good, because remember, 4 15s makes a 60, right? On the clock, 15, 15, 15, 15 gives you 60. 126 is 2 60s, right? So that'd be 8. That leaves you with 6. And of course, 15 into 60 is 4. So that means apparently the X, which I called student then, would be 284 student tickets, which is what you should have gotten, not for X, but for your student answer. How many got 284 for the student answer? Well, we should. And then if we subtract the 284 from the 395, we should have gotten 111 adult tickets as well, which is what you should have gotten for X, 111? Questions?
I think it's because I stick with you guys in the bottom. That's probably where all the pieces.
Questions on this? Be careful in your multiplying and dividing. But you see, we might have made your math just a teeny bit easier. All right. We're going to come back to some word problems here in just a moment. We are finally going to move off of the number of each, value of each, because I feel like by now y'all should have that pretty good. Yeah, you're not going to forget that. All right, page 417. Let's go over the rest of the homework, then we'll get back to different word problems for a change. Woot. Don't want word problems to get boring or anything. It's too easy. Give me something more challenging, Mr. Nadasky. Okay, I hear you. Page 417, you did numbers 2 through 20, the even in the review section. Number 2, Maddie, what'd you get for your answer? Good. You take out the common factor 3x, factor out the difference of squares into the 2x plus 5, 2x minus 5. Number 4, Noah.
5x negative 12 times 5x negative 12.
Good, or 5x negative 12 squared. But since we're in the fraction section, we're used to now just separating the two of them so it's easier to cancel one away potentially. Number 6, Gavin.
3x times quantity x negative 2 times quantity x positive 4.
Good, 3x, the common factor, times x negative 2, x positive 4. Number 8, Maddie. Good, 3x negative 1 times 5x positive 2. Number 10, Noah.
3x positive 5 times x positive 3.
Good, 3x positive 5 times x positive 3. How many had all 5 of those correct? Excellent. Number 12, there's a common factor in the denominator. Should have pulled out the y squared out of the denominator. Question for you. Once you've pulled out the y squared, and you see a y squared in the top, what are the y squares going to do, class? Cancel. Is there anything else that can cancel? So the reason we factor, listen to me now, the reason we factor is so we can cancel. But if there ain't nothing else that can cancel anyway, why would we keep on factoring? See how the lazy brain works. So yeah, I get as far as the y squared, to get y squared positive 3y positive 2. I'm like, yeah, I could factor that, but why? There ain't nothing else up here. See it? Now I do need to specify that y, well, y squared, but y squared is simply 2 different y's, correct? Each y individually cannot equal 0. That said, if you did factor it, y positive 2, y positive 1, certainly not wrong, and probably this is what we would have had. It's just in this case, we couldn't cancel anything else anyway. How many got this answer? Number 14, what'd you get for your answer, Noah?
1 over x plus 2.
Good, and we didn't have to say that x can't equal negative 2 because we still had a factor of x plus 2 in the denominator. Just 1 over x positive 2. Number 16, Gavin.
X negative 5 over x positive 3 and x cannot equal negative 1.
Great job. X negative 5 over x positive 3 where x cannot equal negative 1. Number 18, Maddie, in the numerator, what do we have to do with that thing? Good. We're going to have to factor the numerator by grouping. So we're going to look at the first couple of terms, and what's common in the first couple terms? 2a, leaving you with, and in the next couple of terms, it's b times m plus n. And then we realize, well, now I've got two terms, 1, 2, and each term has m plus n in it, so if you pull the m plus n out of each term, it leaves you with. How many did the correct factoring by grouping? It's been a little while since we've done that. Okay, excellent, good. And in the denominator, Maddie, really straightforward, just pull out the, leave you with the, and now you can cancel away the, leave you with an answer of 2a positive b over 3, where m plus n can't equal 0, so we could say that m can't equal negative n. And there's our answer. How many have that for number 18? Excellent. Number 20, I need to pull out a common factor of 4 in the top. I need to pull out a common factor of 6 in the denominator. Of course, backwards FOIL, sum and difference, cancel some stuff away. What was your answer on number 20, Noah?
2 times m plus 3 times, over 3 times m plus 2. And m cannot equal 2.
Good. 2 times m plus 3 over 3 times m plus 2, where m cannot equal a positive 2. Did anyone get all 5 of those correct? 12 through 20 even. Okay, good. A couple of you did. Noah just missed
12.
just number 12. I was waiting for you to just say just missed 1 or just missed 2. Just missed 12. No, he means number 12. All right. I missed 12 out of 5 problems. We go back to our math illiteracy poster. All right, questions on this? All right, turn over to page 82. Turn back to page 82 now. And last year in pre-algebra, you talked about travel. Talked about some things moving, people driving, people flying, people running, people riding bikes, you know, a ball flying through the air. And we know that as something moves, things can move at different speeds. But you also know that speed is determined by a distance traveled and a time of travel, right? This is why when you're driving down the highway, you see the speed limit sign, it's like 55 miles per hour. A distance divided by a time. So if speed is distance divided by time, this literal equation, if we were to multiply both sides by time, I would get this statement that speed times time equals distance. We're going to begin working a set of word problems that involve distance, speed, and time. And if you'll remember that speed times time equals distance, you'll notice this is the same chart setup we just used for number, value, and total value. Do you see it? So we're going to begin working some problems, and this is going to be the basic setup here. We're going to build off of what we already did, but now apply it to travel problems. Read problem 24 for us, if you would, Noah.
An automobile driver traveled the first part of a 400-mile trip at an average rate of 50 miles per hour. Upon reaching an interstate route, his average speed increased to 60 miles per hour. His total travel time was 7 hours. How far had he traveled when he reached the interstate route?
The first thing you're going to want to do is you're going to want to look at this, and you're going to want to say, how many unknowns do we have? Well, this one trip was broken into 2 parts. Do you see it? There's the first part of the trip, and then there's the interstate route. Do you see it? He travels the first part of the trip, that's to get to the interstate, and that's a long way. And then after he gets to the interstate, he travels on the interstate, right? And most of you, how many families travel somewhere for Christmas, Thanksgiving? You know what I'm talking about. You have to travel on some back roads or maybe some smaller highways. Then you get to the interstate, and it's like, yes, Now I can just put, for a driver, it's like, yeah, I can just put the car on cruise, and we're just gonna go for a while. No more turns, no more turn signals, no more red lights, no more anything, just on the highway. You know what we're talking about, okay? So here we've got two unknowns. Do this with me, there are two seats. We've got the first part of the trip that it talks about, which is the getting to the interstate, and then we've got the interstate part of the trip. We have the first part of the trip, and we have the interstate part of the trip. Now, it leaves us to assume that his destination is right off the interstate, because it doesn't mention an after the interstate part of the trip, but maybe that really is how it goes for him. Now, you're going to want to look and see, are the speeds clearly spelled out for me, or is the time clearly spelled out for me? What does it say about the speeds here, Maddie? And do you see how that's clearly spelled out? We don't have to wonder. It's kind of like the value of each for most of our problems. Clearly spelled out. First part of the trip was at 50 miles per hour. Interstate part of the trip was at 60 miles per hour. There's no unknowns there. It's just very clearly delineated, right? Like in the last problem we just did a few moments ago, the prices of the adult and student tickets were clearly spelled out. What isn't clearly spelled out is the time of the trip. Now, we are told about time. What is told to us about time, Gavin? The total time was 7 hours. Now, some of that 7 hours was spent getting to the interstate. Some of it was spent on the interstate. We don't know how much of each, right? But if the total is 7, class, I can represent one of these as, and the other as total minus x, or in this case, 7 minus x, right? Which one do you suppose would choose to be x, class? Interstate, because it's the bigger value. And then the first part of the trip could be the 7 minus x, total time minus x. Do you see how this is really just like what we just did? It's same song, second verse, just different application, I suppose. And if you know the speed and you know the time, if you multiply, you get the distance. So how far did he travel the first part of the trip here, Noah? How far did he travel on the interstate, Maddie? And if we take the total distance traveled getting to the interstate, and we take the total distance traveled on the interstate, it should equal, class, the total distance of the whole trip. Well, that's our last number we haven't used yet. What was the total distance of the whole trip, class? So what do you suppose the equation's going to be here, Gavin? 350 minus 50x plus 60x equals 400. There we go. How many think of the same thing as Gavin? So you're looking at this, you're like, this is a brand new word problem. I've never seen this before, and you pretty much already know how to do it. Right? Because it's so similar to what we were just doing. We do need to go and combine some like terms here, class. 10x, and at the same time, let's move the 350 over as a negative. That should be a little easier than the last subtraction we had to do. 50, good. And that'll give us x is equal to 5. All right, now, what is 5? 5 is an amount of time. It's an amount of time. So the interstate time is 5, or we would say 5 hours. That means the first part of the trip took 2 hours. But realize, that's not what the problem was asking. The problem did not ask, how long did he travel on the interstate? Or how much time was spent getting to the interstate? Rather, the question was, how far had he traveled when he reached the interstate? In other words, what is the distance of the first part of the trip? We're looking for this number right here, and there's 2 ways to get it. Method number 1 is to plug in the 5 and solve. Method number 2 is to multiply the 50 times the 2 you've already got, which gives us, so apparently he traveled 100 miles trying to get to the interstate. Man, that's a long way to travel before you even hit an interstate. Dang. Maybe he lives in Wyoming or something. It's like this one interstate goes right through the middle of the state. You live anywhere else, you gotta travel forever to get there. I'm like, man, it's a long way. Anyway, that's just because we're in the South and there's interstates everywhere down here. Anyway, questions on this? All right, let's take a look at number 83, or 23, right before that one. And Maddie, read this one. All right. So we have two different trips mentioned, don't we? The first trip mentioned, class, is the trip there, and the next is the trip back, right? The return trip and the trip there. So we'll go there and back. Remembering that when we say back, that's when the book mentions the return, right? Okay, so there and back. Which of these is clearly spelled out? The speed of there and back, or the time of there and back? The speeds, right? Once again, and this won't always be the case, by the way, but it's the speeds that are clearly spelled out. Going there, the bus goes 50 miles an hour, and on the way back, it travels 45. Now again, this is average speed. It doesn't mean it's 50 and they never deviate from it, right? So perhaps traffic was a little bit more congested. There were a few more slowdowns. Maybe they didn't hit very many red lights going there, but they hit more red lights coming back, right? Because it's not a big difference. It's not like rush hour traffic in Atlanta where going there is 50 and on the way back is 5, you know? Yeah, anyway. What about the time? What does it tell me about the time there or the time back? Maddie? Coming back took half hour longer. Well, that's a comparative word, right? Half an hour longer than what, class? Getting there. So do you see that this time it's clearly spelled out which one must be X? The getting there must be X. And coming back took half an hour longer, so we would say, Maddie, ooh, not half hour, not half as much, half longer, half more than. X plus a half, or maybe we say X plus 0.5. Do we see that? Half an hour more time required to get back. Well, if I know the speed of each, and I have the time of each represented, I can get the distance of each. What is the distance getting there, class? 50x. And the trip back, ooh, this is going to be fun. Brave volunteer to handle this distribution of the 45. Let me work it out on paper first so I don't look stupid in front of Brecken. Brecken's not going to judge. He's a good man. There we go, Brecken. I said it. It's on YouTube. Save that little clip. Play it over and over every time you feel low self-esteem. Mr. Jesse says I'm a good... Anyway, you can tell I don't struggle with self-esteem because I feel like he should think that my opinion's worth something. All right? Anyway, what do we get when we distribute the 45? Gavin?
45 plus 22.5.
There we go. 45x plus 22.5. Now, here's the kicker. There's not another number in the problem. Normally, we set up the equation by looking at, okay, what number haven't we used yet? Normally, we would say, all right, this total money plus this total money equals the total money, right? Or we say, like the last problem, total distance plus total distance equals total distance. And give me that. And this is where the distance problems deviate slightly. There's not another number, and here's why. We start out at point A, we go to point B. There's a distance there. I don't know what it is. It's 50x. Then we come back. I don't know what that distance is. It's 45x plus 22 and a half. But what do I know about the distance there and the distance back? They're going to be the same, because the cities didn't move, right? Now, assuming you didn't change the route or something, right? Distance there, distance back, they're the same. And so my equation here, and this is where you have to employ a little bit more logical thought, is you have to figure out that the equation is one distance in this problem, not every problem, this problem, equals the other distance. Do you see it? Well, let's solve. This time I'm not going to combine the x's because they're on different sides. I have to get rid of one. Which one do I get rid of, Maddie? And when I get rid of it, I move it over as to get is equal to 22.5. We then divide both sides by the 5. And be careful not to lose the decimal point when you do it. 5 goes into 22, class. 4 times with, but now we're after the decimal, so put a decimal in the answer. 5 goes into 25. 5, so we end up with x is equal to 4.5. What does x represent, class? The time it took to get there. It took 4.5 hours to get there. It took a half hour longer to get back. How much time did it take to get back? 5 hours. But that's not what the problem asks. It didn't say how long it take to get there or how long it take to get back. What did the problem ask? Find the distance. How do you find distance? Speed times time. Or speed times time. Either one. At your seats, find how far apart are these two cities. Similar setup, and then on the tail end, a little bit more thought, and I have to go into these problems. Brecken throws his hands up in despair. Brecken's like, how did he see that? You have a webcam on your computer, Brecken. Come on, man. I'm kidding. I just know. Thinking. Now he's laughing. He's like, I didn't do that at all. Mr. Deskey's being stupid. I rolled over and puked again. It's not that bad. Class, what's the distance between the cities? 225 miles. 225 miles apart. Questions on these. We're going to continue working on these over the next several days so that you can get an idea of when to do what, but ultimately it boils down to you thinking through the setup of the equation. The setup of the box should be easy. The setup of the equation will require some thought, and sometimes a picture can help. All right, let's go ahead and move back to fractions. Now, next section in your notes, now that we have talked about how to reduce fractions, how to simplify fractions, we want to begin looking at how to actually work with fractions, perform various mathematical operations with these algebraic fractions. And we're going to start with what I consider to be the easiest mathematical operation, multiplication. So next section in your notes, multiplying fractions. Multiplying fractions. I want to take you back to when you were in 4th grade? Maybe 3rd grade, but definitely by 4th grade you knew this. Your teacher would have taught you that when you multiply fractions, it's really, really easy. You multiply the numerators and you multiply the denominators. So class, my numerator would be, and my denominator would be 27. Yay! Isn't that easy, class? And everybody was happy. And then the teacher showed you 2/3 times 7/10 and said, all right, class, let's multiply the numerators. And let's multiply the denominators. And she said, but sometimes, class, you're going to have to reduce your answer because we don't want to leave a fraction like this that has something that can be divided out, a common factor. And so we could reduce the 14/30ths, class, down to 7/15ths, and that would be our answer. But then the teacher got all of you smiling again and said, but there's a shortcut. We don't have to wait till the end to reduce. We can save ourselves some work. How many of you want to save yourself some work? Which actually isn't a bad thing to say because it's like mathematicians are lazy. 4th grade version. All right, so we're going to save ourselves some work. Who am I picking on here? Who's your 4th grade teacher?
My grandma.
Your grandma. All right, great. Always have in trouble with grandma. All right, you know, you lose some, you lose some. So, so your teacher would have told you, really what we're doing is we're dividing a 2 out of the top and bottom here. But if you find a numerator number that has the same factor, I don't know, maybe that's how she said it, as a denominator number, you could have canceled them before you even multiplied it. It makes the multiplication easier. So she would have pointed out, notice in the 2 and the 10, there's a 2 in both of them. You can take a 2 out of the 2 class, and a 2 out of the 10. And now when you multiply, you get 7/15. You don't have to reduce at the end. This is something she called canceling, right? Do you remember this? And by canceling, you don't have to reduce, because canceling is essentially reducing while you work the problem. Make sense? The key is we can only cancel factors. We can never cancel terms. We don't say, well, let's cancel the 3 with the 7 and leave ourselves with a 4. No, 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 no. You divide out or factor out, right? So write this down. 6a over 9 times 5b over 8a squared. 6a over 9 times 5b over 8a squared. Your first step to reducing fractions, remembering that we want to do some canceling, right? And we can only cancel factors. We can never cancel terms. Step number 1 is going to be to factor. Factor completely. Now, in this problem, you can't factor anything, okay? But normally that'll be our first step, is to factor completely. Step number 2 is going to be to cancel any numerator with any denominator. You cannot cancel a 3 with a 9 here because they're both denominators. But that which is up can cancel with that which is down. Numerator factor can cancel with the denominator factor. So there are some things I can cancel here. Gavin, tell me one thing you see you could cancel.
6 and 8.
Okay, what can cancel with the 6 and the 8?
2.
A 2 cancels out, right? To leave me with
3a and 4a squared.
There we go. We get a 3 and a 4 when we cancel out of the 6 and the 8. Give me another thing you see that would cancel here. Noah? The a can cancel with one of the a's in the a squared to give me 3 up here and then 4a down here. So the a and a squared cancel to give me nothing here and then the a down here. There is one more thing that cancels, Maddie. And here's where sometimes elementary teachers do their kids a disservice, because they teach you to cross cancel. They teach you to look diagonally. But any numerator with any denominator, including up and down, the 3 and the 9, right? Any numerator with any denominator do cancel, so that would leave me now with a 1 and 3. So my second step is to cancel any numerator with any denominator. Now, technically when you cancel up and down, you're just reducing, period. Like you're just reducing that fraction. But diagonally and up and down works, just not side to side, because that'd be denominator with denominator. Step number 3 is to multiply across. I've got a 1 times a 5b, class, 5b. Very good, no. I've got a 3 times a 4a, class, 12a. Very good, Maddie. At least you tried, Noah. Appreciate the participation. We'll give you a participation trophy, because that's the day we live in. All right. And we end up with 5b over 12a. Do we see how in algebra we're really doing what we were doing in arithmetic? It is canceling any numerator with any denominator. It just could involve letters, possibly. Write this example down. 3x negative 6 over x squared positive 2x positive 1 times x squared negative 1 over 3. 3x negative 6 over x squared positive 2x positive 1 times x squared negative 1 over 3. When you see polynomials, you've got to factor. That's our first step. Here, class, pull out the 3 that's common to leave us with. Down here, backwards FOIL into anyone? Good, x plus 1 squared or x plus 1, x plus 1. The x squared minus 1 factors into? Good, x plus 1, x minus 1, the sum and difference. And the 3's a monomial. Monomials don't factor. Once we've factored, now we can cancel. Doesn't this sound an awful lot like reducing fractions? Yeah, okay. And so what are some things we see that would cancel here? X plus 1's cancel. 3's cancel. Anything else?
No.
No, the x plus 1 does not cancel with the x minus 1. So our third step then is to multiply everything that's left. However, we don't actually have to FOIL stuff back together again. Instead, we're just going to basically write down everything that's left. In the numerator, I have an x negative 2 and an x negative 1. In the denominator, I have an x positive 1. And there's my answer. Now, normally, if something cancels out of a denominator, we need to say that it's not equal to 0. Well, we have an x plus 1 that canceled, but we still have another one sitting here. We have a 3 that canceled, but 3 already can't equal 0. So this would simply be our answer here. Gavin, you had your hand up a moment ago. Question, or did I answer it for you?
Figured it out.
You figured it out. Okay, excellent. Questions on this? All right. One more, and then we'll call it good for today. Write this one down. X squared negative x negative 6 over 3x squared positive 18x positive 24 times 6x positive 24 over 6 negative 2x. All right, factor your first numerator. Call it when you've got it. Good, x negative 3x positive 2. All right, now the next one we need to pull out a common factor of, oh sorry, you're going across. You're going over to the next numerator. Pull out a common factor of 6 to leave you with, all right, sorry, I was working my way down. All right, now coming down here, I was like, 6, come on, Noah. Okay, you're looking at that one. At least that's what I'm going to say. All right, looking down here, start with a common factor of 3 to get x squared positive 6x positive 8. And then backwards FOIL, call it when you've got it. Good. 3 times x plus 4 times x plus 2. All right. Now, something doesn't look right about the last denominator. It's not in descending order. So let's flip-flop it. Let's write it instead, Maddie, as the 2x is negative, but the 6 is positive, so does that make sense? All right, but I now need to factor out what class? Negative 2. And that's going to leave me with x negative 3, because as you factor out the negative, it changes both of the signs. All right, and now we get to see what cancels. Well, notice x negative 3's cancel. X positive 2's cancel. X positive 4's cancel. 3 and 6 cancel to give me a 1 and 2. 2 and 2 cancel. Everything cancels except one thing, the negative sign. And you might recall that in multiplication, if everything cancels, your answer is 1. So in this case, negative 1. Where some mathematicians would argue that you ought to specify that x cannot be negative 4, negative 2, or positive 3. What x? Your extra credit this evening, page 82, word problem 25. Page 82, word problem 25.